just means where P shows the sum over logs log P. Okay. So this just means that the product of primes P less than x, this is x as equal to P for x. Earlier we saw that this is less than 4 coordinates by x. And now the prime of the theorem is equivalent to this product of the primes which are less than equal to x. The product of them is P as equal to for x. That was the observation that for this we are thankful to Chebyshev. That is he observed that it's perfect to just estimate the product of primes less than equal to x. And that's how it got estimates for not this one, but the thing that theta x is bounded from above and below. Okay, so this was Chebyshev. And he obtained this result even before pretty much we are working by intelligence. So how to proceed to we'll proceed through this. And today's class is a preparation for this. So suppose I must be this integral psi x minus x by x squared dx over the range from 1 to infinity. Okay? So we'll show that this is equivalent to the convergence of this integral. And to show that this is convergent, well, not equivalent to x, that if this integral converges, that would imply that this is true. So suppose this integral converges and this fails. Let's make some contradiction. So here the statement that we are trying to prove is that if the integral converges, then psi x is asymptotic from x. So we are assuming this and we are assuming this is not true. Now what it means that it is not true? The limit as t goes to infinity psi x by x, this is, so if this is true, that means this limit is equal to 1, and this is equal to say this, right? Now if this is not true, that means the lim sup, either the lim sup is greater than 1 plus some epsilon for some fixed epsilon, whereas the lim inf is less than some 1 minus some epsilon for some reasons. So let's try to demonstrate. Centralized to me. So this means if psi x is not asymptotic to x, then either lim sup psi x x is greater than or equal to 1 plus epsilon, or for some epsilon, or lim inf psi x by x is equal to 1 minus epsilon, or some epsilon greater than 0. Okay. going to show that neither of these can be true if this integral has to converge. In the first case, this one, psi x is larger than or equal to 1 plus epsilon times x. Well, this limits of this level equal to this, that means that they exist, excuse me. So this one means there are infinitely many ways such that this happens. There exists. Such that we have this. So now note that if this integral converges, then that would imply this converges. That means its tail part goes to 0, right? So that would imply that for sufficiently large, there are infinitely many a. So you can take a sufficiently large. That implies for a sufficiently large, the integration from a to infinity psi x minus x by x squared dx, and as well as integral from say a times 1 plus epsilon or 1 plus epsilon a to infinity psi x minus x by x squared dx are as small as we wish. So, in other words, for a sufficiently large, both of them are smaller than any given quantity. Any given integral. That means if we take the difference, that is also only to 0, right? So take the integral from a to infinity psi x minus x by x squared dx minus the integral from 1 plus epsilon times a to infinity psi x minus x by x squared dx. Then since both of them are going to 0, this should go to 0. This integral is nothing but the integral from a to 1 plus epsilon times a psi x minus x by x squared dx. Okay. Now note that psi x is an implicit function. So over this range from a to minus a, and all the values that you can take are larger than psi of a. So this is larger than or equal to a times 1 plus psi a. to be one such a for which this happens. One such a which is like the voice of your life might be considered greater because of this one. Okay, you can just mention it. So this one is what we're doing is that doing this integral, but now we are going to do something. That is here x is moving from a to 1 plus epsilon x, right? So we will replace x with some t times a, okay, where t is varying from 1 to 1 plus epsilon. Substitute x by t times where t ranges over 1 to 1 plus epsilon. Then this integral is equal to the integration from a 1 plus epsilon a psi of a minus a by d squared and dx, where dx should be replaced by a times dt. So note that also we should use here this fact that this is larger than 1 plus epsilon times t. So this is larger than 8 times 1 plus epsilon t, and this is 1 plus epsilon t minus a by d squared times a.
Range should be 1 to 1 plus epsilon.
Ah, right, yeah, thanks a lot. And also here. One to 1 plus epsilon, and this one is also from 1 to 1 plus epsilon. Note that all the a's cancel. Get cancelled from the right hand side. So get that this is the integral from 1 to 1 plus epsilon 1 plus epsilon minus t by t squared dt. And each of the terms, for each t is a positive thing. And you can easily integrate that to get some constant which is depending only on epsilon, which is positive, because each of the terms are positive. And you can actually compute it. It should be something like epsilon squared or epsilon squared by 2 and epsilon squared by 3. That's etc. So this is going to be positive constant. Similarly, in the other case, okay, how far can we actually copy the other case? Up to here, because the sign of the equal will only change. So this is S2. For S2, there will be infinitely many A's in this, such that psi A is less than or equal to 1 minus epsilon. Okay. And then we have this one, that is again these two are going to 0, and we are now considering this integral, but the limit should also change. It was in the first place we were integrated from a to 1 plus epsilon a, and now we integrate from 1 minus epsilon a to a. The same. Now we will again do the substitution, that is substitute h by TA, and TA in the range will generally be from 1 minus epsilon to 1. Okay. And here we will consider this integral. Again, things will cancel. Oh, okay. Wait. Before we put anything here, now this is psi a minus TA, and what we will write that psi a is less than equal to 1 minus epsilon t, right? And again, since it's an increasing function, everything else in this range would have value less than psi a. So I mean, if you just try that.
Is I of 1 minus epsilon.
Right. Thanks a lot. This integral radio integral, right? Oh, this is the psi of t. Oh, right. Yeah. Here, it should be less than or equal to psi of t minus x by x squared. And you know that psi of a is now less than or equal to 1 minus epsilon times a. So we just plug this in here. And we get that. And everything changes, right? In the second case, so this will be 1 minus epsilon. And the relation of derivative has already changed. And then this constant that we are getting, note that now t is varying from 1 minus epsilon to 1. Right? So the integrand below is just t squared. Up, in the numerator you are getting negative terms. Right? And you are integrating negative terms, all the terms are all the for each of the values of the t, you are getting negative thing here, which you are integrating. So the constant that you would get, say c dash t, c dash epsilon, is going to be a negative one, which depends only on this epsilon. Okay? So in either case, you are getting some constant depending on this epsilon, which is either positive or negative. Whereas we are taking this difference of this two integrals, and both of these terms are converging where? Converging to 0. So thus we are getting contradiction. So this thing is, if maybe, so after C epsilon we wipe this part out. Okay, we are going to start a new so it's not like everyone on board. So if limit by x by x is not equal to 1, then say that the difference of these integrals does not go to 0. If we choose A to be such that we are choosing A to be from the exceptional set. So set psi of A is greater than 1 plus epsilon A, or psi of A is less than equal to 1 minus epsilon. And this inequality guarantees an infinite supply of such keys. So that means all we have to do is to show that this integral converges to get to prove prime integral.
Sir,
Yes.
so in both the cases, the difference will be 1 plus epsilon in the case 2 also.
Case 2 also.
In case 1, we get a difference when the limit is 1 plus epsilon A. For case 2, it is fixed 1 plus epsilon A or 1 minus epsilon.
So for the case 2, that is this one,
Yes, it is the difference.
the difference between this and this. Yes, note that as A goes to 0, sorry, this one is, oh, okay, right. So, thanks a lot for pointing this out. Okay. That is, it's not exactly this integral. I wanted to say that we are doing something similar, but here, in the second case, we are considering this one. Thanks a lot. So then, the different, even then the difference of this and this are going to be negatives are going to 0 because this lower limits are going to be infinite. Okay, right. So either this one or the thing that we just wrote, 1 minus epsilon times A to infinity psi x minus x by x squared x minus integral from A to infinity psi x minus x by x squared dx. Okay? So either this is not going to 0 as it goes to infinity, or this one is not equal to 0 in the second case. And that proves that the integral cannot converge.
So is that what is the equation?
What do you?
The value of this equation?
Exactly. Could you please just see how the body is looking like? It's noisy. Okay, so we will switch off this. We do it normally. So how to go about this? It is, so till now, let's write down the steps here. So this is integral now to show that this integral converges. Okay. And we go via boundaries. So here we proceed to this theorem that if G is a function that is analytic in the region real part of S greater than 1, and if there exists a function if x which is big of x, that is which is of the size x, or I mean it's bounded by some constant x, such that g of x is given by the integral 1 to infinity fx by x power 1 plus x dx. Then g of well, this for all is real part of s greater than 1, then g of 1 is equal to 1 to infinity dx by x squared dx. So we go by this term and you see what is our fx, this one and this one. So it is exactly the form fx by x squared. So we proceed to exert this term first, and then what will be the task to show that xi x minus x by x comma plus s, that is analytic in this region real part of s greater than 1. And that way the zero of this definition. That doesn't have zeros, but line real part of this greater than 1. That can follow. So how should we proceed with this? First we do a substitution. So we put z such that substitute 1 plus z for x and e power p for x. And define g of z as, but we just work with f of z. F of x is equal to fx by x in particular that since x is big of x, that means capital X is bounded. And let g of z going to restate this theorem in terms of capital T and small capital F. Then this theorem becomes if Gz is a function that is analytic for all Z with real part of Z greater than equal to 0 and in the region, so put that in the region real part of S greater than equal to 1, this will correspond to real part of Z greater than equal to 0. If there exists a function, a boundary function now, because we are defining this one. Bounded function if such that what should we write now? Here are the upper part of the code. If there is a boundary function f such that g of z is equal to the integral from where? Now the range of the integral will change, right? X was running from 1 to infinity, so t would run from 0 to infinity. And fx by x was f. So now it will be if of whatever value we take. Okay, f of t is there because we have replaced e for t for x. So let's write down and then see. So f of et, that means you have already taken there f of x by x, right? And also having x is so dx, we just differentiate this and get dt. And here, then this extra 1 plus x, what was it? Here. Now 1 is gone and we are just writing this s. Okay, that is, okay, let's write it out here. So, f of et, okay, let's also do this first. And just write down the equation here. Not immediately here. So this is g of z. We are just writing g of s for g of z. So let's write in terms of fx first. Okay, this is fx by x power 1 plus s dx. Let's substitute already e power t there for x by t. So 1 equals because we have not changed the value yet, and now we are doing 0 to infinity f e power t, and below we have e power t times 1 plus s here e power t dt. Okay. E power t gets cancelled with e power t there. Right. Okay. No, we are getting yeah. E power t is remains there.
f of x by x is f of x
F of x
by x is f of x.
yes we have not substituted a capital F yet. We are doing one by one. So at first we are substituting x here, and then we will substitute the capital F. So that we have, we get track of all the equalities. That is, so how many equalities are there? This will cancel. So equality with this equality, this will cancel, and it will be equalities.
Why did you get rid of the S?
Yes.
Why did you get rid of the S?
Yes. In the next step we will be getting rid of it. Yeah, actually that helps because immediately we can put z here.
Yeah.
Thank you. So 0 to infinity. This is if e power t by over ez, and here there is another e power t dt. Okay. So we could have cancelled it here, but we are not cancelling it. We are just giving e power t z. But this one, I mean, for if we equated f of it should be f of et by e power t. Okay. So yes, 1 plus 1 plus z is yes, right? Ah, right. Okay, thanks a lot. Yeah, so it's the opposite. So this is 1 plus s, and then this will be t power. Yeah. Higher, louder, please. That is okay. We cancel it. All right. And then it is e power ts, and then right. So for s we write here 1 plus z, right? And then this f of et we are going for t. This one we just write f for f et for t. 0 to infinity f et by ez. So gt is this one, and we are assuming that there is a boundary function f such that this integral, I mean gz is given by this for all z with real part of z greater than equal to, sorry, strictly greater than 0. Okay. Then we would like to show that G0 so it's still the theorem statement. We are extending this theorem. So then g of 0 is given by this integral from 0 to infinity well, z is equal to 0. So this one is just 1. So this is if et. So we're going to show this. That is, if g is such that it satisfies this function, then g of 0 will be given by this. And how should we proceed? Then as I said, this is a with two complex analysis, and the things that we often use in complex analysis is contour initiated. We'll get, and we'll also define a contour over which G will, well, yeah, over which you will be analytic, and then there will be a pole inside that you can guess where the single pole will be, and we'll use Cauchy-Schwarz theorem to get this. So in our step of proof is to integrate this function from 0 to some t. truncating these functions, so we're taking just a truncation of for et like e power ez ut. And note that this function is an integer function. It doesn't have any problem at anywhere. So our task is then to show that this transition, if you take the limit t goes to infinity of gt, say this limit is converges to g0, g0. Okay. Because since this function is analytic everywhere, that means you can put the put 0 here. Wait a minute. No, we are trying to show this. Excuse me. Yes. Because at any other place, both the functions are so for real part of z is still greater than 0. Both the functions are analytic, so we don't have any problem. But in this set, we have to get this. That is the limit at 0 of gt is where g0 will be. How should we proceed with this? So this is equivalent to show that the limit t goes to infinity g0 minus gt0 this is equal to 0. Right? Now we want to construct some component of this then. Like this. So take the inner circle. And then note that the function g is analytic everywhere on the right of the circle. And also here you can make you can shift this slightly to some delta scale. Or some data distance, small distance data. It's right here. So that is still analytic on that data. Right? Yeah, for a second, right? What is given? G is a function that is analytic for all states which is real part of set greater than 26. Right? That means on this, suppose we are considering only this part, that is this unit distance, the distance started by this unit circle. And you know that on this line, which is a disconnect, that means around every point there exists some neighborhood. Sorry, almost all of them are true. I want to say is that you can cover them, cover this region with some neighborhood of these points in which the function is analytic. And take the, well, since it's a compact region, there is a finite subcompactor. And now, take the smallest radius of the open ball around the point, in which this is the function. Okay. So, if that smallest radius is delta, then that means you can shift this line a little bit to delta. And on delta, this function g continues to be analytic. So that's what we're doing. We're defining this continuous. And now, over this contour, the first thing that we is that now we will integrate over this contour and we are having a problem at 0. Okay, so we can do like integral of dz minus dz. This is acting on the boundary plate. And consider this, and then consider the residue of this. But that won't work. So take this as a homework to think about the ladder or the acceleration. This a direct approach. Let us just divide this by z. I am thinking of this as not simply, excuse me. I wanted to write the integral over this contour. What you see. I think that this is giving you the required reciprocity. G0 minus G0t. So if you could show that this integral converges to 0, then it will be done. But nevertheless, that makes life quite difficult. So we have to use some kernel here. Not just this one, but so. But note it down. And what is the problem with the direct approach? Please try to think of this. Instead, we will consider this integral 1/2 integral over the 1 to c dz minus gt z times e power z t. Then 1 by z plus z by r times dz by z. What do you mean? Let's see how I write them directly. This is 1 by z and this is r by z. Looks fine. Yeah. So this it will be actually done some picture. Let's see what happens to the this kernel should be well behaved at 0. Let's see what happens at 0. No, not on 0 here. I mean, yeah, at 0 this part would only give you T0 and G0. And this thing should be equal to 1. Now check this, there is a 1 by z here, so that would make a problem, and then it cannot be there, so that is. Okay. If the entire thing goes to 0, it should be just 1 plus z by r by z squared. Let's see whether this will work. No, I thought. Z squared cannot count the denominator either because we are considering the simple pole of simple pole at 0. So yeah, this will work fine. Let's see. If you put z equal to 0 there, this is 1. And if you put z equal to 0 there, this is 1 also. Okay. So if you consider the residue at point 0, we just get G0 minus G0. And this is the kernel that actually makes life much easier. This kind was introduced by Newman in his which is till now the shortest proof of Feynman theorem. But nonetheless, all the proofs of Feynman theorem, except possibly the proof by Reyes and Selberg, real and proof. Except that, if all the other known proofs goes via the zeta function is having no zeros on the real line, on the line that real particles is one. And instead with that, the proof by Reyes and Selberg. It's not by Reyes and Selberg because it was actually an argument by Selberg in which we just made observation. Yes. And
This is controversial.
yes. Right.
Seriously controversial.
Yeah. So.
But later Selberg changed the proof little bit.
Yes. Yeah. Selberg
Did the change?
Selberg actually did it. Took a path which was not. He didn't took the path that research stayed as positive, but nonetheless he had some other way to complete the proof. And indeed, this is controversial because Reyes got. At the end, it is actually a paper published by Selberg, and there is no written documentation, I think, of the proof by Reyes. Or is there?
We had a fight.
No, there is some written documents.
But it's never
But
published.
Selberg refused to put his name there, so.
So yeah, let's come back to this proof. So now what we are going to do? Okay, if we consider this integral over this contour, then this, that is g0t minus gt0, would come as its residual because this is the polarization. G0 minus gt0 by Cauchy's theorem because the integrand is analytic everywhere on path on which we are. So it is analytic everywhere except for its pole. Right. So now what we are going to show is that this integral points to 0 as t goes to 0. That is what we show. And for that, we will take, now we consider it on different parts, like this R and this R, this part, the part delta. And also, we'll consider gt tau on this one because it will be easier to consider gt tau on the negative part of the circle. And then since this function is sort of everywhere, we can say that the integral from over this is the same as the integral over this one of g. Okay, and then so that is the plan for proceeding with this theorem. And once we prove it, then it would remain to show that the function that we are considering, that is, we did all of this because we wanted to show that this integral converges and instead, if this converges, this is basically fulfilling the role of this G0 here. So we have to show that it converges. This would be implied by, and the properties of these would be implied by the fact that this is analytic for real purpose case. So once we prove this theorem, we will proceed to prove this one. So that's all for now. We start in the afternoon next week.